So this is the first exercise sheet. It starts out with the definition of some simple sets, which we will need for the second exercise then also to make some combinations. It's just a little training now for building composite sets like universal set, intersection, and so on. So there's a little problem right at the beginning for myself, which is the symbol capital N. As you all know, this is the natural numbers, and actually there are two different notations used in the literature. One of them is that I wrote it here, that N denotes the non-negative integers, including the 0. But some people, also myself, regularly use this symbol for the positive integers, so that 0 would be excluded. Now the question is, which notation did Martin use, your main lecturer? And I think he used this notation. Can anybody confirm this?
Yes.
Okay, right? So it means the
Yes.
non-negative integers. Then if this is not his notation probably, but then you could, for example, say n greater 0 is then, this would be the positive integers. But anyway, there are different notations for this. So we have a consensus that the 0 is included, and therefore I think it's easy. The set A is the following, and I would normally put in every single element, but there I used a little abbreviation. Okay, so of course, if x is lower than 10, but a natural number, it starts with 0, and then in ascending order, we have 1, 2, 3, and so on till 9. That's fine. Then I would like you to help me and just tell me what should set B be like. What are the elements? So now if I read, the square of x is equal to 16. This time we have real numbers, which includes especially also negative numbers, of course. So what is the lowest element of this set?
-4.
We have the -4 because this quadratic equation has two different solutions. There's the negative and the positive square root. That's fine. And then the next, I use commas as a separator. Okay, you could also use semicolon, but I think commas are okay. And then again,
4.
Yeah, 4. And any more?
No.
Right, because it's an equation and has two solutions. Of course, these sets are constructed so that they all contain exclusively integers, so that we can easily combine them. So the third one.
Sorry, I have a question.
Yes, please.
Can we find the exercise sheet on Moodle or something?
No, because actually there's only one exercise sheet now, this one, and I didn't originally plan to use exercise sheets, but more to take the exercises on the fly from different sources. Okay, like to be spontaneous and to just reacting to what you're doing at the moment, which stuff should be emphasized. So, but if we keep this mode, then I would try to supply the sheets beforehand. But of course, afterwards it's no problem. This one I can upload it, and I will. Okay.
Okay, thank you.
And and also I will upload sometime, not always immediately. I will upload this note here. Yeah, what I'm writing, these our written solutions you will get as a PDF also. Yeah, so you don't necessarily need to keep writing everything. You can do it. Some like it, but you needn't. Okay. So then, yeah, this should be easy. Everything between 4 and 11, but both limit values are excluded, which means we're starting 5, and then it goes on 6, 7, 8, 9, but also 10. A little bit similar to set A. And for set D, we see, and now it's the case that X lies between 0 and 29, excluded both, no, but exclusively, you could say. But it must be divisible by 4. An integer, which means, yeah, I forgot to mention, these are the integers, of course, signed integers, so negative numbers would be allowed, but we see this interval contains no negative numbers. In this case, it's also allowed, but again, we have only the interval lies in the positive region. So we just look and see 0 is excluded. So the first number here inside this interval, integer number divisible by 4, is 4. Pardon? You said 4, right? So then I count upwards. I take the multiples of 4, of course, 8, 12, 16, 20, 24, and of course I must stop with 28, which is the largest of these inside this interval. So that's fine. We have 4 sets, and I would say I just copy this. I can remove this sign here. I just copy them to the next page, and then it goes on. Second. So that's just for looking at it, so that we can reuse our result. Anyway, this is a little bit, yeah, so that's fine. I'll just delete this here. So there we are. These sets, as you see, it's just combinations of our two most important set operators, which are the unit set and the intersection set. We also know that these are equivalent to the corresponding logical operators in the propositional logic, which will be interesting if we compare transformations in both areas or combinations. For logical purposes, to change or to reduce the notation, which is possible in some cases, it could as well be done inside the logical notation as inside the set theory notation. So there's a perfect analogy between these two fields. That's a big advantage. Anyway, just tell me if I construct the unit set, the union, we should say. What did I say before? Did I say unification? I don't know, but I think union is sufficient to say. What's the term used by Martin? Can anybody tell me?
Unification.
Unification. So yeah, you could also say union. It's almost the same term. So that seems to be fine, because we just put everything. You know, this symbol can be interpreted like an open bag, where you can put something in, and we put everything in that we find. And logically speaking, this would mean an OR, you remember, because it's sufficient if an element belongs to set A or to set B, is sufficient for being contained in the unification set. So this is the logical view on the same thing. I'll try to keep sorting the elements in ascending order. So you just tell me, what's the first one?
-4.
Right. And then, of course, we have those smaller natural numbers, 0, 1, 2, 3. Now, the 4 is contained twice here as well as here, as well as here, yeah, in both sets, but it's better, I think, to put it here so that we can see it. Now, the question is, well, I just make a proposal. I write down 4 again, and then I go on. Do you agree with this method? Because it's here and here, so we have it twice. Is that fine?
No.
Thanks. Because sometimes I need a contradiction. You must not hesitate to contradict me. Of course, it was a test, yeah. Because it's very important. There are no duplicates in set theory. You could have them. You could define them, but for good reasons, one doesn't use duplicates. You can, if you think of Venn diagrams, which you know with these signs, and then if an element lies, for example, it lies in 2 sets at the same time, this would be set A and set B. Now, of course, this is something different now. This is about intersection, but it's better to interpret this as like the set A encircles this element and others, and set B encircles it too. So, but this doesn't mean that the element gets cloned. It exists only once. So it's like independent of the construction of sets. And that's, of course, that makes sense because the natural number 4 needn't exist twice to be useful. So that's quite a good convention to say that no duplicates exist. Fine. And then it goes on, of course, with, yeah, that's probably, I will abbreviate again. So then everything until 9, the -4 was the first, and the 4 is contained in both, but it appears only once. No question. So what do I do if, I mean, without using any rules, which is not directly necessary, if I combine intersection symbol with unification symbol here inside, well, first of all, brackets are useful or even important because there is no real and clear priority between these operations. That means if you think of the distributive laws, they are valid in both ways. It's not like in algebra, in regular algebra, where you usually have the stronger operation outside, and then you must put the weaker operation like addition or something in bracket, in parentheses, because it's weaker. Yeah. So this is a little bit different here. Here's sort of the strongness between these both is the same. So we must decide what we are doing. Anyway, can we do this without an intermediate step? Can we try? In our heads, we just build the union set of B and C. So we take care that we use every number that is contained here and here. And then we just look for because intersection symbol means the common elements, like denoted here. We just look for the common elements. So that's not too hard. In A, contained are numbers from 0 to 9. So I pick up every number from these both sets that's also in the range from 0 to 9. So -4 is not, of course, but 4 surely is. And we could do this in different ways, graphically or even by transforming this expression, but let's just do it by hand. And you disagree if I miss something? Please tell me what's the next element.
5.
Right. And then I suppose it goes on. 6. And you tell me when to stop.
Stop.
Yeah, thanks. That's right, because the 10 is here, but it's not in A.
Yeah.
So it's not really a problem to find them. Should be right, as far as I see. Then, let's make it complete. What's the intersection between A and C? Looking here.
8, 9.
And here. Like, right, I heard 5. Okay, intersect B. Is my voice loud and clear, or too loud, or too?
It's A intersects C, not B.
Oh, yes, right. Thanks. Sorry. Am I speaking? Is my voice loud enough, or is it too loud?
It's clear.
It's clear.
It's perfect.
Good, yes.
Thanks. So then, which elements are common? Which are the common elements between set A and set C? I can see that. Yeah, right. 5 is
5 to 9.
what I heard. Right. Everything from 5 to 9. Now let's speed up a bit because I find that you have perfectly understood everything. So A, unification C. So that it seems we start out with 0, then when we reach the 5, we can just go on with the elements of C or take them from here. But anyway, we must include 0 to 4 for sure, but also the 10. That's the main issue. Okay, seems, if I looked correctly, yeah. And so we have 0, 1, and then I this time I would abbreviate again, and it goes to 9 and to 10. That's it. 5. Help me. B intersection D.
It's B union D.
Sorry, did I said intersection, right?
Oh.
So we just put them together again. That's similar to before. I thought B intersection.
And from -4, yeah.
Right.
4, 8, 12.
Yes, 4 is the common element. It appears only once, and then we take all the elements of D, correct. And then I may abbreviate here because I don't know. I put it there. Because it's not very clear what the scheme is if the 0 is missing. So that's fine. So now we have perhaps something more interesting, a little bit more interesting. We must intersect, yeah, I write it down, A with B in parentheses. And then we unite this with C intersect D, which results
4 and
what?
8.
Pardon?
4 and 8.
Okay, could you give a short explanation?
Yes, A intersect B, the common element is only 4.
Right, because you just look at this as it were one set, right?
Yes.
Or no, you don't. You look for the common elements because this is the intersection. Yeah. So the 4. What did you say? The 4 is the only
common element.
Right. And here.
And here it's 8. The only.
Right. And that's it, right?
Yes.
Perfect. So it's only 2 elements in the end.
Yes, 4 and 8.
4 and 8. That's right. Very good.
Can I ask a question?
Yeah, please.
In this question, in this particular question, normally there's a mathematical order between multiplication and plus, right? So is it the same as unification and the other one?
This is a very good question, but actually I answered it some minutes ago, but probably you didn't get it there. I was talking about here when I said it's important to use parentheses, although both operators have the same strength. There's no priority between and. This is what I meant. Okay, and or. But the parentheses are important because if I change them, I get something different. Okay.
Yes.
Yeah, that's clear. And so interestingly, it's not like in regular algebra where addition is weaker than multiplication, where there's a clear priority. There's no priority. This can be seen very well if you look at the distributive laws in set theory. There are two versions of distributive law, and I can just, because I think this is not in the exercises, I can just put it here for a second. You remember if I have, how did we do it? Yeah, for example, I have A intersect B union C, then I can do something like removing the brackets, which is in this case A intersect B, and then, can you tell me?
Unification in bracket A
Right.
intersect C.
So this is very similar to what we are used to do when we remove the brackets in regular algebra, right? But well, I will try to explain.
Unification. Not.
Yeah,
not
I see.
Unification.
Sorry. I have difficulties at the rim for writing rim. Anyway, but the other variant is analogous. So that's the same rule with exchanged operations. That's a hint at the fact that these operations are hierarchically at the same stage. Okay, that's what I wanted to emphasize here. So now it's correct, I think. Yeah. Distributive laws.
So if there was no brackets, do we just do them in order?
Now that's yeah, right. That's right. If there are no brackets, you take the order from left to right. There's no other way of doing it. But it's bad style not to use brackets. But don't mix it up with the case that you're using only one kind of operation, right? Because then we have the associative law, which says here I can put my brackets as I want. So it doesn't matter. Also with a, union B, union C. Here it's associative. Yeah, you understand the difference? If at the moment when you mix up the operations, you should really use parentheses. Here you needn't, because it's twice the same operation. And the associative law is valid only in these two cases. Is that clear?
Yes.
Okay, fine. So then, but it's a good question. What do you do if there's just written A intersect B union C? The only chance you have is go from left to right. I don't even know if this is really clearly prescribed. Yeah, I don't know if there's a fixed rule for that. We should find out. Okay, 7. You might ask Martin also.
We already did 7. It was.
Yeah, that's right. And I think that that's just, yeah, that's a mistake. I would say, because it's more interesting, we take A intersect B. Is it more interesting? No, not really. But okay, let's take it, and then we see the only common element is
4.
Yeah, so that's it. That's enough of these little simple operations. So we have made it. and then we could just switch to tautologies. I guess this term was explained in the lecture, but I'm not sure. So it's better to define it in short. You may have heard of it. We call a propositional logic formula a tautology if it is itself, it's always true, which means the formula cannot get false in any way. And important is, how do you check this? You must read it in a special way. This happens regardless of the valuation you use for the propositional variables. Okay, so that means, for example, if I have three, I call them inputs sometimes. Okay, the propositional variables are the input of the formula. And you know the thing, you know the topic here with truth tables. That's for example, this is the, you could say that's the most secure method to write down the complete truth table and then check every single line and look for the result. And if it's always a one, a logical one in the right column, then it's per definition it's a tautology. In philosophy, we must take care a little bit. This term is sometimes used a little differently. So one could say a tautology is normally it's a self-fulfilling statement. There are some examples from natural language, like it's hard to find them when you need them, but I think you can invent one by yourself. Something like, if I say, I'm not sure. I don't find a good example from natural language, but there are plenty of them. So something like where you say it's obvious. It's so obvious that it's not even worth anything. And I think there's a certain difference because in logic, for example, take case 2. If this were true, if this implication were true, in any case, it would be a tautology, but it still would deliver some sort of information in the sense that it's a valid rule, a rule that you can use to transform other expressions or to take, to draw conclusions and things like that. So you understand that means formally we are just looking for we are just looking if any of these statements is always true or if it isn't. If it's always true, it's a tautology. If not, it's not. And that's what we want to find out. So the examples are perhaps not too interesting or too intelligent, whatever. You can judge yourself. I take P and now you see what it is. It's negation of negation P. Usually I use I personally use big letters for logic variables and use this bar symbol for the negation. That's my my preferred notation, but this time I use just the same notation as here. And this is the one you are used today, I think. Is it clear? I mean, it should be clear without a proof that negation cancels itself. So if I have a double negation, I get the original. So since this is P, and then it's written equivalent to P, it seems to be, there's some more thing. It's called, I'll write it down. So we have P and P equivalent to P. And now, what would you say, what is this? How is it called and how can it be replaced?
Just P.
Yeah, it's just P, and there's special term for this. Can somebody remember? Just write it here. Sorry, it's wrong color. Take this. 4. Nobody remembers? It's a strange Latin word. It's called idempotency. I think Martin wrote idempotent as an adjective, but perhaps there was an N here, but I'm sure it's called idem. Idem means same, and it's a little strange thing, perhaps. What it means is that you get the same result anytime you repeat a procedure. But hard to explain why this is called an idempotency. You would say it's because P and P always takes on the same value as P alone. So anyway, this is how it's called. And so in the end, we end up with P equivalent P. And now, if we want to make sure that this is a tautology, we could, for example, make a truth table with only one input, which is P. So that's, as you know, that's a truth table with only 2 rows. That makes it quite easy. P can either be 0 or 1. I will always use this notation for false and true positive logic. Okay. You can also use capital T, capital F, capital T this way. But you know, the truth table of the equivalence, that's important. Because in the end, what we get here is, it's like 0 equivalent 0. But I don't write this here. I make it this way. Our expression takes on 1 here and here. That's the detailed analysis. Okay. You could also say, okay, it's obvious that a logical variable is equivalent to itself, but more in detail, it means that if it's 0, it takes the 0 on both sides, and if it's 1, it also takes 0 on both sides. What we see now is that this is a tautology because it gets true independently from the valuation of its inputs, and the only input is P. So regardless of what I take for P, I get a 1 at the output. So that was the more detailed explanation, right? And then the second, I thought to myself, it would be nice to really check it with a truth table so that we have a little exercise about truth tables here. And that's what I would propose to do now. I prepared it. We have 2 inputs, P and Q. And the question is whether it's not so hard to see, but we want to prove it by hand. P, logical OR, you know this. P or Q implies P and Q. Spontaneously, what would you say? Is this always true or is it not? Just by thinking.
Yes. Sorry, yes, it's true.
So that would mean every time P or Q is fulfilled, it follows that P and Q are fulfilled. Okay, I see. But perhaps you didn't check all the cases or think in a different direction. I have expected that you say no, it's not true, but it's not. Perhaps it's not so easy to see at once. So that's why it's a good idea to take the truth table. What do? We take a column for P, 1 for Q. My style or my convention is to take the inputs in ascending order. If you read them as a binary number, you understand what I mean? 0, 0 is a binary 0. 0, 1 is a binary 1. This is a binary 2 and a binary 3. You know, 1 times 2 plus 1. So that's a certain convention that is often used. I think I remember that in Martin's notation or in his notes, there was these 2 lines were exchanged, which is not forbidden at all. But I always use this order. Right? It's not really clear how to do it, but I think it has its own scheme. Okay, so that's fine. Just don't mix up these two lines in your mind. So now this is just short notation for the OR. The OR compound by putting P and Q together, by combining them. So this is a compound. Call it a compound, okay? But we know that the OR operation leads to 0 only if both sides are false. In all other cases, you get 1. Why? Because it's sufficient if one of the inputs is true for OR to get true, and it's allowed that both get true because this is an inclusive OR. This is what we use in regular logic, right? It's also important if you take the analogy to set theory, because the unification set corresponds to this OR, and actually it corresponds to the inclusive OR. You remember we had some elements in the unification set before here. The first example, it was the 4. The 4 is an element which lies in both sets, A and B, and anyway it belongs to the unification set. And logically speaking, this would mean if we replace this by an OR, we have the inclusive case. This is the inclusive case, and it's important that it's valid. Otherwise, we will get a problem. Okay, so far, so good. Then next, this is the AND truth table, well known. We know that the AND operation is only valid, only true in the last row. You see the difference? This is not complementary. Sometimes you think this is the opposite of that, but of course it's not. If you compare, there are some rows where both are the same, 0, 0 and 1, 1, and somewhere they are different. And now that's the problem. We evaluate this, and now this is short notation. I ask you, are there something written in the chat? Yeah, a little interruption. Lucas? Ah, okay, I see. It's a little hard for me to answer the chat because it's easier with the audio channel, you know. Yes. Yeah, as I said, the notes will be uploaded in Moodle. From time to time, I try to do it every time, but it can take a while sometimes. So what I mean here is the implication, and we have to remember the truth table for this operation. You know, this is a little exotic, but it's important to understand. And you can tell me, is it fulfilled in the first row?
Yes.
Yes, it is. Explanation. We have a feedback at the moment. Acoustic. It's not so serious, but okay. So I explain it. In this case, you know, the premise is the left side. The premise is the OR compound. The conclusion is the right side here. It's the AND compound, P and Q. So now, if the premise is false, the conclusion can also be false, and still the implication is true. That's important because it's you could say it's the passive case. The premise is not responsible if it doesn't get true. It's not responsible for the conclusion to be true or false. Just there's a very good formulation in Martin's notes, which says the premise is sufficient for the conclusion. On the other hand, the conclusion is necessary for the premise. So in this case, we see that if this were 1, this would have to be 1 also. So there is one contradiction case in the logical implication. Now we can call it the contradiction case. And this is the case when the premise is true, but the conclusion fails. Conclusion goes false. Why is this a problem? Because the premise should guarantee the conclusion to be true. That's it. That's, you could say, that's its task, its job. The job of the premise is, if it gets true, it must make sure that the conclusion also gets true. So when the premise is sufficient for the conclusion, something's wrong here. Also, no, the other case is not here. But yeah, that means we have a contradiction as well here as well as here, and everything's fine again in the last row, which means that this implication is not even true. So it's not a general rule that you could use. Okay, so this is, if I mark these zeros, say this is the reason why this is no tautology. Oh, I forgot to say, this is in the end, I do it this way. This is a tautology, but this is no tautology. Interestingly, perhaps you were thinking of the other case when you answered that you think it's true. In any case, did I write it correctly? Tautology, I think so. Here, what would be the case if we exchange premise and conclusion? So if there would be written, just for a moment, imagine it would say P and Q implies P or Q.
And this time it will be a tautology.
Right. Suddenly it's a tautology because we get these two values exchanged, and then the premise would in the end is false, but the conclusion gets true, which is an absolutely allowed case, as I told you. And so in the end we get ones here and here in every row. What you see here is, if this were the case, then we would have to call it a tautology, although it would also be a useful rule for doing logic. So it's a little dangerous to overinterpret the term tautology. It's defined as above, and we used it accordingly. So that's fine. Okay. 3. This is funny. I think we don't write it down downside because it's too much to write. I would say we use the space here. Just a second. I would take all of this a little below. So what do we do with this? What can we say about the expression? Oh, sorry. Oh, what happened? Yeah. What's the wrong tool? Yeah. Now, what about this? Any ideas? We could think of the idempotency from before, which it is not. It looks a little bit similar, but it's not where I must say P and P is the same as P. P or P is also the same as P. You know, that's the case. These are the two idempotent cases, idempotencies, right? But in this case, we have P or its opposite. What do you say about that?
It means it's everything.
Interesting idea. Everything means because we must replace it by something. And in a certain way, it's right what you just said. Everything means this includes all cases that can occur. Yeah, if you think the way that you say, okay, P, either P is true or its opposite is true. Either P is true or it's false, and if it's false, then not P gets true. With other words, we always have the inclusive and the exclusive case of the OR. We always have the case that the both sides have different truth values. If this is one, it's like 1 or 0, or it could be 0 or 1. But in any case, it's true, because the OR, for the OR, it's sufficient if one of the inputs is true. And that's why I can replace this with a logical 1. I can say it's always true. And that's important, because what comes next is now or something complicated. So, or I just take a question mark here, because I wouldn't immediately know what the truth value is of this. Look at this. It says Q implies, and then parentheses around means Q implies this whole expression, which is equivalence between R implies S and T. So first of all, we have Q, R, S, T. We have 4 more new logical variables, and we have no idea how this connection should take place if T is totally independent of the others. You see? Because it almost can't be that the value of T would always follow this one here, because they have nothing to do beforehand with each other. Anyway, it doesn't matter at all. Why doesn't it matter?
Because we have 1 or anything.
Right, 1 or anything, and this equals
1.
Yeah, thanks. That's it. Because the one side is already fulfilled. So because this is a logical OR, it means that since the left-hand side is always true, the right-hand side doesn't matter anymore. And that's why this is also a tautology. It's quite fun.